Go ahead and take a look at that. No, you can hang on to it. Okay, so there's a starter question here, and it is, what is a rational number? What is a rational number? It's fabulous.
I think it's a whole number.
Whole numbers are a specific type of rational number. Okay, whole numbers are rational numbers. What's that? Pi, you're right. Pi is not a rational number. What's the root word? Sorry, what? That is correct. Okay. What's the root word of the word rational?
Ratio.
Ratio. Ratio is a, what is it? It's a fraction. Rational number is a fancy word for numbers that can be written as fractions. So, numbers that can be written as fractions, as ratios. So, the number 2, rational. The number -3/2, rational. Christopher's example of pi, not rational because you can't write it as a fraction. Okay, it's a number that goes on forever, a decimal that goes on forever and never repeats. Okay, now you could take pi and put it over 1. Okay, but when we say it's going to be a rational number, it's got to be one integer over another integer. So that begs the question, can anybody tell me what an integer is? Don't say anything out loud. Think for just a second. What is an integer? There's a really easy way to describe what an integer is. Okay, who thinks they can tell us? Zach?
I think one would guess, but it's like a countable number, because like you can count of it.
Has something to do with that. Clayton?
Whole numbers, positive or negative.
Positive or negative whole numbers, and one other thing. What's in between the positives and negatives? Zero. That's the best way to describe what integers are. Positive and negative whole numbers, including 0. So numbers that we really like. So if you had to put these in a list, integers, rational numbers, and irrational numbers, which of those 3 are the nicest ones to work with? Integers. Next, rational. Worst, irrational. Numbers like radical 17. No fun to work with because they're irrational. Okay? So keep those straight. At least those 3. Integers, positive and negative whole numbers, including 0. Rationals, numbers that can be written as fractions. Not our favorite, but they're better than irrational numbers like pi or e or radical 2. Yeah.
So would like 1/3 be considered irrational because it goes on forever?
Well, okay, hold on just a second. Okay, missed a key part of what I said. Is 1/3 a rational number?
Yes.
It is, because it's a number that can be written as a fraction, right? I mean, 1/3 is a fraction. It's a decimal. If we wrote it down as its decimal equivalent, it goes on forever, but what's the part that Zach missed? Not picking on you there, Zach. What is it?
That it's not repeating.
Right, okay. If it's a repeating decimal, then it's a rational number, okay? So the number 0.66 repeated, 2/3, okay? 0.11111111, 1/9, okay? So if they go on forever and they repeat, they're rational numbers, okay? You would have done some of those in elementary school. You do long division problems and you get these big long decimals and they start to repeat. Okay, Zach didn't. He ignored the homework that day.
I never liked division.
We'll go back and have your teacher correct that. Okay. All right, so most of the polynomials that we dealt with in 5.1, they were already factored. So there's something really nice when they're already factored. You can look at it, you can tell what the zeros are. We just need to multiply them together to figure out what the leading term is, so we can tell the degree, so we can tell the end behavior is the terminology that we use there. So if it's already factored, then the x-intercepts are really easy to find, all right? And the end behavior is relatively easy to find as well. But if it's not factored, then it becomes a little bit of a pain in order to figure out what the zeros are, especially if it's a 3rd degree polynomial or a 4th degree or a 5th degree. If those aren't factored, they're a huge pain. So in this section, what we're going to start talking about is we're going to explore polynomials a little bit more, even if they're not factored, we're going to be able to find what all the zeros are. We're going to be able to figure out the overall shape, whether it touches or crosses and all that sort of stuff. So this is going to add to the things that you're able to factor. In 1010, we could only factor 4-term polynomials, difference of cubes, sum of cubes, difference of squares and stuff like that. Easy trinomials, hard trinomials, grouping, take out common factors. Those were the rules that you learned. But polynomials are so important and they have so many applications, we need to be able to take really ugly looking polynomials and figure out, hey, what does this look like? Where does it cross the x-axis? Where does it cross the y-axis? If it crosses the x-axis, does it touch or does it cross? Okay? All of those sorts of things that we looked at yesterday, only this time they're not going to be factored. So, recall from R6, if the remainder is 0, then the divisor is a blank of the dividend. What word goes there? Okay, factor. So if the remainder is 0, then we know we've divided by something that's a factor because it went in evenly. Okay? Now, with polynomials, we're going to learn some tools that allow us to figure out whether or not it's a factor, and we don't always have to do long division. Okay? And sometimes we don't even have to do synthetic division, although synthetic division has its advantages. So we're going to go over several theorems that are going to help us understand polynomials a little bit better. Their names are ugly. They're very wordy. Okay? Some of this isn't very fun. Okay? But by the time you get done with this, you're going to be able to do some pretty amazing things. You're going to be able to take big, ugly polynomials, and you're going to be able to describe nearly every facet of its behavior. Okay? So again, we're just adding to our toolbox and understanding how this math works. So here's the first one. This is called the Remainder Theorem. So we're going to read this and then we're going to think about it. This is going to take 2 days to get through this section. So you don't have any homework from 5.5 tonight, other than you need to think about what we talked about in class so we can build on that tomorrow. Understand? So it might be good to go back and review the notes when you go home tonight. So the Remainder Theorem says, let f be a polynomial function. So we've got a polynomial function. If f of x is divided by x minus c, so if we take that polynomial and divide by a nice little linear factor, then the remainder is f of c. So the remainder is the function value at x equals c. So think about it this way. Normally, we have to plug the number into the function to figure out what the function value is. The remainder theorem says that the remainder is the same as the function value. Okay, now we're not going to take time to prove this. Okay, if this were, if you were all getting degrees in math, we'd be doing an analysis class or something like that. We'd actually prove this. We're just going to take this theorem for granted. But what it says is the remainder is exactly the same as the function value. So if you divide and you get a remainder, you know that's the same thing as if you plug that number into the function to figure out what the function value is. You know, the y value, basically. Okay? So it says, find the remainder if we take this polynomial and divide it by each one of these factors using synthetic division. Okay? So we're going to do synthetic division. So this is going to be a 3 in the box. What am I looking for here? We did synthetic division. We just corrected R6. What am I looking for? I'm looking to make sure that it's in what order? Descending order, and that all the powers are represented. If they're not, I'm going to put a little placeholder in. So I'm going to put a 1, a -4, a 0, and a -5. You with me? Draw the little line, draw the little box. I'm going to say this several times. What are we hoping for right here?
0.
We're hoping for a 0 because that means this would be a factor. So let's check and see. Bring down, multiply, add, that's a -1, multiply, that's a -3, add, that's a -3, multiply, that's a -9, right? Add those together, -14. Now, the remainder, doesn't matter that it's not 0, the remainder is good news here, okay? So let's take this one. We're going to put what in the box? -2 in the box. Again, I'm going to write down the same ones. 1, -4, 0, -5. Bring down, multiply, add, multiply. We got here 12. Add, multiply, -24. So I get -29 altogether, right? Okay. Make any mistakes? Okay. So that's example 1 star. And it says, find the remainder using synthetic division. And this next one says, find the remainder using the remainder theorem. So what we're going to do is, we're going to figure out what f of 3 is. Wait just a second. Do I need to actually plug this in? We figured it out. What is f of 3? Should be -14. And what is f of, well, let's see. What number goes here? -2. It's the same one as went in the box. And what is that function value? Should be -29. Now, just for the heck of it, let's just make sure that this actually works. Let's plug in a 3. So if I plug in a 3, I end up with 27 minus, this would be -4 times 9, so that's going to be -36 minus 5. So this gives me a -9 minus 5 more is -14. So did it work? It does. So the remainder is the same as the function value at that particular point. Now, the thing you do need to keep track of is, remember, this is x minus c, so that it's the number that goes in the box. It's the opposite of the number that would be in the factor, so to speak. Does that make sense? Okay, a little weird, but that's pretty easy, isn't it? So you can either find the function value by plugging it in, which we already know you could do, but you could also find the function value by finding the remainder. Just do synthetic division. Does that make sense? Now, the cool part is, depending on how long the polynomial is and how big the exponents are, synthetic division could actually be easier. Because if you think about it, all you're doing is multiplying, adding, multiplying, adding, multiplying, adding. All pretty easy operations. Here you've got to, I mean, what if this was x to the 7th? You've got to take 3, raise it to the 7th. You have to grab a calculator for that. Whereas on this, you wouldn't need to do that. Any questions there? Okay, so that's called the remainder theorem. The remainder theorem simply says this. The remainder is the function value at x equals c. Okay, that's what that one says. Okay, let's take a look at the next theorem. I need to summarize this first of all. Okay, the remainder theorem gives us 2 ways to determine if x minus c is a factor. The first thing is we can divide to see if the remainder is, what do we want the remainder to be? 0. Okay. Or we can find f of c, we can plug it in and see if f of c is 0. Because if the function value is 0, stop and think for just a second. Remember, a lot of thinking with this, not very difficult math. If I plug a number in and the function value is 0, where would I plot that point? On the x-axis, right? So it would have to be an x-intercept, a 0, solution, root, whatever you want to call it. Good there? Okay, so that's the remainder theorem all summarized up. The next one is called the factor theorem. Okay, the factor theorem helps us understand how factors, zeros, and x-intercepts are related. Now remember, I've got a little box down here. Zeros, x-intercepts, solutions, roots, those are all pretty well used interchangeably. So depending on who your teacher is or what book you're using or different things like that, those will be different. So if f of c is equal to 0, then x minus c is a factor. If x minus c is a factor of f of x, then f of c would equal 0. So this is pretty closely related. Okay, it's kind of the idea that we've been talking about here for a second. If the function value is 0, then that's got to be on the x-axis, which means it would have to correspond to a factor of x minus that particular number. If x minus that particular number is a factor, then the function value has to be 0. That would put it on the x-axis. So this is the same thing said in 2 different ways. If you know the function value is 0, you know you've got a factor. If you've got a factor, you know the function value's got to be 0. See how that works? Yes, looking for a shaking of the heads, except for Christopher, because his head's down if he shakes his head. it would hit the table and that wouldn't feel good. Okay, so what this means is we can use the blank to find the factors.
The zero?
The zeros. We can use the zeros to find the factors, and we can use the factors to find the zeros. So we've got this going both ways. Now what I'm hoping is we've kind of talked about this or just broached the topic several times as we've gone through the last couple weeks. I'm hoping that we can kind of put this all together. So let's flip the page over and look at example number 2. It says, first, find the x-intercepts on the graph. Difficult problem? Piece of cake. We've got a picture of what this looks like. It crosses here, here, and here. So the x-intercept would be -2, the x-intercept would be 1, and the x-intercept would be 4. Please tell me I counted right. So, part A taken care of. State the factor that would have produced each of the x-intercepts. Or we probably should say sketch or state one possibility for each one of the factors. So if -2 is a 0, what factor should that have come from? X plus 2. And this one? X minus 1. And this one? X minus 4. Any questions there? Okay, now you don't need to write this down, but I do want you to watch. If x equals -2, this is why we call it a 0. What happens if I move this to the other side? There's my factor that would produce a 0. If I move this to the other side, it would be x minus 1 equals 0. And if I move that to the other side, it would be x minus 4 equals 0. See why we call them zeros? Or at least another reason. The other reason is the y-coordinate is 0. It's on the x-axis. The function value is 0. Okay. Is that all right? Okay. Last part says, find a polynomial that could produce the graph.
So don't
You just times them all together. So we'd say f of x equals x plus 2, x minus 1, x minus 4, and then I'd multiply them all together. So if I were going to multiply these, and there are a couple problems where you do have to do this. The reason we're going to do this is just this morning I was teaching a calculus class. We did a problem just like this. And for some people it was difficult to keep track of how you multiply all three of these together. So what I would do is I'd multiply the first two together. When you multiply them together, you get x squared plus x minus 2. Is that right? Then I'm going to multiply it by x minus 4. If I do that, I'm going to get x to the third plus x squared minus 2x. That's what I get when I multiply the x through. Then I'm going to multiply everything by -4. So that's going to be -4x squared minus 4x and then plus 8. So if I were to write it like a true polynomial, so I can see a power function plus another power function plus another power function, this is what I'd have. X cubed minus 3x squared minus 6x minus 8, and this would be the answer to the last part. Really, that's the biggest pain in the butt, isn't it? Oh, is it a plus 8? Thanks. Thank you. Okay. That's the biggest pain in the butt, isn't it? Finding the x-intercept is easy. Figuring out the factors is relatively easy. And then we just have to multiply them together to make the polynomial. Now, what degree is this polynomial? Third degree polynomial. Okay? So it should look like x cubed. It should start down here and end up here, does it? Yes, it does. How many turning points can a degree 3 polynomial have?
2.
Up to 2. It doesn't have to have 2, but it can have up to 2. 1, 2. Okay? What's the multiplicity of every one of these zeros? 1. So at every one of those zeros, it should cross. Cross here, cross there, cross there. Everything's good, matches up with what we went over yesterday. Any questions? Sure? Okay, relatively easy? Okay, let's take a look at the next one. This one says, use the factor theorem to determine whether the function f of x equals 2x cubed minus x squared plus 2x minus 3 has the following factors. Now, here's what's a little bit of a struggle, and I'll be totally honest with you. If somebody says, use the remainder theorem, I have to sit there and think, well, wait a minute, what was the remainder theorem again? And if they say, use the factor theorem, I've got to think about what the names are. I know what they mean, I know how to use them. it's keeping the name straight. So let's take a look back up here at the factor theorem. It says if f of c is equal to 0, so if the function value when you plug the number in is 0, then it's a factor. It also says if it's a factor, then f of c's got to be 0. So let's take a look at this one. So we've got to somehow establish that the function value is 0. What am I going to plug in? A 1. So I'm going to figure out what is f of 1. What am I hoping for? I'm hoping for 0. Well, if I plug in a 1, I get a 2, a minus 1, a plus a 2, and a minus 3. What do I get? I get a 0. What does that mean about this? This right here is, yes, it's a factor. Okay? Any questions? Okay. Clayton, what am I going to check right here? How am I going to do that?
You plug it in or division.
Okay. If I were to plug it in, what would I plug in?
-3.
Very good. Plug in a -3. Now, that's a bit of a pain. Plugging in -3, let's see what I get here. -3 cubed is -27 times 2 is -54. -3 squared is going to be 9 with a negative in front, so that's going to be a -9. This is going to be a -6 and a -3. Now, stop and take a good look. Should I even bother adding those up? No. What I know is it's going to be negative, so nope, not a factor. Now, Clayton said something kind of interesting. He said you could plug in -3, and what was the other thing you said?
Division.
We could go ahead and do division. Okay? Either one is fine. In the long run, it's usually going to be better to do division, especially if you can do synthetic division, and you'll see why, especially in the next section in 5.6. Okay? Any questions? Okay. So if you need to look back at what the names are, so you know whether you're using the factor theorem or the remainder theorem, that's totally fine. There are a couple other factors that we want to take a look at that are going to help us figure out the zeros of a polynomial. So the first one is this. A polynomial cannot have more real zeros than its degree. Now the reason we say real zeros is because we're talking about where it crosses the x-axis. Those have to be real numbers. They can't be imaginary numbers. They can't have eyes in them. Okay? So, how many real zeros can this have?
3.
Okay. Can't have more real zeros than its degree. So this is degree 3. So up to 3 real zeros. Now, it doesn't say it has to have 3. It just says it can have up to that many. What degree is this?
6.
So up to 6 real zeros. And this one? Up to 1. Okay, now this is important right here. This theorem, unlike the other two that we've done, it doesn't help us find zeros and it doesn't help us find factors. It just tells us how many we're looking for. Because over the next couple sections, you're going to be given some degree 6 polynomials and you're going to be told to find all the real zeros, or maybe all the zeros, whether they're real or imaginary. That'll happen in the next section. Okay, so we'll wait till later this week to do that. Okay, but on this one, if I find 3, I know I'm done. On this one, if I find 6 of them, I know I'm done. I can stop right there. I don't have to keep looking for any more than the number of the degree. Okay, any questions? Okay, are there any questions on anything we've done so far? So the remainder theorem, the factor theorem, and the number of real zeros. Yeah.
So for the real zeros,
Uh-huh.
do they correlate with the turning points?
To some extent they do. Okay, the degree will help you help tell you how many times it can cross the x-axis, and it'll help you figure out how many times it can turn. How many times it can turn is always 1 less than the degree. How many times it can cross the x-axis is the same as the degree. Okay, so it has something to do with it, but you have to be a little bit careful with that analogy there. Okay, anything else? So the remainder theorem says you can figure out if you find the remainder, that's the same as the function value. The factor theorem kind of says if the function value is 0, then you've got yourself a factor. And if you've got yourself a factor, then the function value's got to be 0. And this one tells us how many we're looking for. This one's probably the easiest, isn't it? Okay, ready? Okay, here's the next one. So I'm going to read this, and then we're going to summarize this just a little bit, and we're going to figure out that this actually isn't as bad as it looks. On some of these problems where you're using this thing called the rational zeros theorem, all you have to do is list a bunch of numbers that are indicated by this theorem. So here's what it says. So I need you to wake up. McKay's going to wake up. Okay, Christopher's lifted his head. That's good. Now his eyes are open. Okay. I need you to think about this for just a minute. We'll summarize it. It is not that bad to use. It's pretty horrible to read. So this says we've got a polynomial function that's degree 1 or higher. So it's degree 1 or 2 or 3 or whatever. Okay? It looks like this big, long, ugly mess. So this is a degree n polynomial. So once we've got a polynomial, and it says each of the coefficients is an integer. Clayton, what's an integer again?
Whole numbers, negative, 0, positive.
Positive and negative whole numbers including 0, okay? Make sure you keep track of that. Integers and rational numbers are important, okay? As long as all of these are integers, positive and negative whole numbers, which they usually are, okay? Then it says if P over Q is in lowest terms and is a rational 0 of F, then P must be a factor of A naught, this one right here, and Q must be a factor of AN, this one right here. Now, here's what we're going to do. We're not going to call this the rational zeros theorem, although if you hear that, that's fine. We're going to call this P and Q stuff. Okay, write that down. The rational zeros theorem is the P and Q stuff. P and Q come from the beginning number and the ending number, the coefficient at the beginning and the constant at the end. Now, P is associated with which one? Careful, take a good look. P must be a factor of the end. So this is P, and that makes this Q. Okay? So we call it the P and Q stuff, but P has to do with the one on the end. Q has to do with the one at the beginning. You with me?
So how come we're not allowed to say the Q and P stuff?
If you want to stay Q and if you want to say Q and P stuff, do you want to change it? We'll say Q and P stuff if you want. Doesn't matter. Q and P, okay, they're in order. We'll call them Q and P. That's probably a good suggestion. Okay, now, the next, we're going to do a bunch of problems and hopefully solidify all of these ideas. So I need your attention just for another more minute, and then it'll get a little more interesting. Okay, what this theorem does is it says if we're going to find the zeros of a polynomial, we're going to find the easy ones first, the easy numbers first. Now, at the beginning of class, we said, well, if you had to rank them, which ones would you rather work with? Integers, rationals, or irrational numbers? What would be best? Integers. Integers are really nice numbers. Okay? Next best? Rational. And worst? Irrational. So we're going to leave those to the end. Integers and rational numbers, fractions. Integers are fractions. We can write them as fractions. So those first two that you said were better, those are rational numbers. So what we're saying here is, and what this theorem allows us to do is, it allows us or helps us find the rational zeros. It helps us find the nice ones first. Okay? So that's usually what I say, is we're going to find the nice ones first. And by nice, we mean ones that are written as fractions. So do you want to find things like this? Or do you want to find ugly zeros like 2 plus radical 3? Neither is the correct answer, apparently. But if you had to do one, and let's say you were given some motivation, enough time and enough money to motivate you, you'd probably want to find 3/2 before you found 2 plus radical 3, right?
Yeah.
Okay. If you get that argument, that's the idea behind the, we're calling it Q and P stuff. That's the idea behind the Q and P stuff. Okay? All right. So, example 5. So go ahead and flip it over. And I'm going to leave this so we can see this. All you have to do on this one is do this. It says list the potential rational zeros. So if there are any nice zeros to this particular polynomial, I'd like you to tell me what they are. What are the possibilities? Okay, so this number right here is, you're right, it is 2. Very good. Okay, it's a Q. And what's the number, the one on the end? It's P. So Q is 2 and P is 6. Here's why I kind of like P and Q rather than Q and P. P has to go on the top, Q has to go on the bottom. So P in this problem, now, all you need is the number. The number 6. You don't really care whether it's positive or negative. What's Q? Q is 2. So P must be a factor of that number on the end, and Q must be a factor of that number on the beginning, the coefficient on the beginning. So here's what I do. I list the factors of 6. 1 goes into 6, 2 goes into 6, 3 goes into 6, 6 goes into 6. What numbers are factors of 2? 1 and 2. So here's P, I put it on the top. Here's Q, I put it on the bottom. I list the factors, and then I do this. Possible rational zeros. They've got to be factors of P over factors of Q. I'll say that again. Factors of P over factors of Q. So it could be 1 over 1. It could be 2 over 1. It could be 3 over 1. It could be 6 over 1.
So just 1, 2, 3, 6.
1, 2, 3, 6. Or I've done every one of these over the factor here of 1. Now I need to do every one of these over 2. So the next one is going to be 1 over 2, 2 over 2, 3 over 2, 6 over 2. You with me so far? Okay, now, this is my list. Now, you're going to get better at this. We'll do a couple more of these. Okay, I'm certainly not going to leave it looking like that. So here's what we're going to write. This number is a 1, put a comma. This number is a 2, put a comma. This number is a 3, put a comma. That number is a 6, put a comma. What about this one? 1/2, put a comma. Do I need to write that again?
No.
It's already on my list. This one? 3/2, not on my list. What's this one? A 3. So these all together, those 6 numbers, are the possible rational zeros almost. The only thing I need to do, remember how we ignored the fact that this was negative and this was positive? Whether it's positive or negative doesn't matter. 1 would go into 6, and so would -1. Okay? So we just put a plus or minus in front of every one of those, and we're done. That's it. That's your list. There's your answer to that problem. You have some problems that ask you to do exactly that. You don't have to do anything with the numbers. You just have to list what they are. Okay? Now, please raise your hand if you have a headache. All right, thank you very much. Okay. It's the goal of math, okay? Especially 1050. Okay, are there any questions? Okay, now, we can make this go a little bit quicker. Okay, but on some of these, that's all you have to do is just go through and list them. Okay, one more thing. How many numbers do I have here? I have 12. Is there any way all 12 of those could be zeros of a degree 3 polynomial? No. But what we're saying is, if there are any nice zeros, they've got to come from this list. Okay, question?
Wait, but there's 12.
Right.
So that's just your answer.
Okay, this just says list them. In a minute, we're going to figure out how to check whether or not they work.
Oh, okay.
Okay? Good? Any questions? Okay, you have problems like that. Let's take a look. Okay, I do want to point out that those last 2 theorems, so we're talking about the rational zeros theorem and the number of real zeros. Okay? They don't find the zeros for us. They don't tell us whether or not it's a zero or not. They just help us produce a list and make finding the nice zeros especially easier. Okay? So we're going to learn to use those rules, those theorems, and we're going to use a lot of algebra in order to figure this stuff out. Okay? Any questions? Okay, that is all the stuff you need to know. Now we just need to figure out how to apply it. So this is problem number 12. It says, use the remainder theorem to find the remainder when f of x is divided by x minus c. Use the factor theorem to determine whether x minus c is a factor of f of x. Very wordy. Here's what it means to do. I want to know whether or not this is a factor of that polynomial right there. The easiest way to do that is try synthetic division, and what are we hoping for a remainder? So put a -3 in the box, -4, 5, 0, and 8. Right? -4, 12, 17, -51, -51. Put those together. That's going to be 153, right? Combine those together. That's going to be 161. You are correct. Okay, we do have that part figured out. Okay, it said use the remainder theorem. So in other words, find the remainder and use that to tell whether or not this is a factor. Is it a factor? Nope. Is that hard? That's a problem on your assignment. That's how they are. They're not all like that, but that's pretty easy, isn't it? Really, isn't this just one tiny step above what you were doing the other day? That's all it is. Okay? It's very good. Okay? But at least you don't have a life vest.
I don't? Are you going to kill me?
Okay. List the potential rational zeros. Do not attempt to find the zeros. What problem is this like?
The one we just did.
The one we did up above. Now, I'm going to show you how so this is how I'd explain it. This is all of the steps involved. This is how I'd actually do this problem. You ready? So I'm going to figure out what P is, and I'm going to write it right here. That's a 6. Q is 4. I'm going to write down a 1, a 2, a 3, and a 6. A 1, a 2, and a 4. Right? Now, I'm not going to bother writing every one of these fractions. That gets a little bit silly. If I take 1, 2, 3, and 6 and put it over 1, what do I get?
1, 2, 3, and 6.
So I'm going to write 1, 2, 3, and 6. And then I'm going to use my head just a little bit. 1 over 2, 1/2. 2 over 2, already in my list. 3 over 2, better add it to the list. 6 over 2, already in the list. 1 over 4, 1 over 4. 2 over 4, 1/2, already in the list. 3 over 4. 6 over 4. 6 over 4, reduce it, 3 over 2, already in the list. So compare the work that we did up here on example 5 with what we've done on problem number 40. Okay? That's a little bit shorter, isn't it? We're not done. What do we need to do, Marissa? All you need to do now is go through and put the plus or minus in front of each one of those, and you've got them. Now, Marissa's beef is, my gosh, how many possibilities are there? 1, 2, 3, 4, 5, 6, 7, 8. 16 possibilities? And we've got a degree 3 polynomial? How many possibly could work? Only 3 of them. That means at least 13 of them don't work. Okay? But again, this is about narrowing down and finding the nice ones first. Now, usually, not always, but usually, the ones toward the beginning of the list work. They're not trying to kill you, honestly. Well, maybe some of you they are. Okay? All right. Any questions? Mhm.
That's all I'm like,
Yeah, but you're not going to have to do all 13 of them.
it takes like hours.
No, it doesn't. No, you'll see.
That is a lot.
Okay. This is where we put everything all together. So on this problem, it says, use the rational zeros theorem. So use this thing. Make a list of ones that might work, so we can find the nice ones first, and then finish it off. We want to find all of them. Okay? It says use the zeros to factor it over the real numbers. So I absolutely guarantee that you're going to have an exam question like this. You're probably going to have a final exam question on something like this. So here's what we do. The first thing is I'd look at this and I'd say, it's a degree 3 polynomial. How many zeros am I looking for? Yeah, there could be up to 3 real zeros. So up to 3 real zeros. Now, if I remember right, I picked a nice one for you. So let's run through and do this. Can you factor that? It's 4 terms. The only way to factor 4 terms is by grouping. You could take an x squared out of here, and you'd be left with an x plus 8, but you can't take anything out of the 2 of those other than a 1. You can't factor this by grouping. So, if all we had were 10-10 skills, we'd be done. You would be stuck. You would not be able to solve that problem.
Well, we have 1050 skills.
Very good. And what is a 1050 skill that we have? If we're going to find 3 real zeros, which ones do you want to find first?
P's and Q's.
P's and Q's. Now, take a good look at this. Tried to be really nice on this problem. What is P?
20.
What is Q?
1.
When Q is 1, that's really nice. Why? There's only one factor. It's 1. So that means the list here is going to be 1 and 2 and 4 and 5 and 10 and 20 with a plus or minus in front of each one of those. So there's our list of possible zeros, real zeros, that is. I'm going to call them nice zeros, okay? So if there are any nice ones, they've got to come from that list. Okay, now, if you're going to check to see whether or not it's a 0, it's usually best to do synthetic division. Except for if it's a 1. If you're trying to see if 1 is a 0, it's usually easier to look at it. So watch what happens. Watch. If I plug in a 1, a positive 1, 1, 8, 11, what do those add up to? Subtract 20, what do you get? Is it a factor? Yes, it is. Here's why plugging it in and finding out, hey, yeah, that's a factor, doesn't really do us a lot of good because we have to go through and divide anyway. So what I know is if I set up synthetic division with a 1 in the box and then do a 1, an 8, an 11, and a negative 20, what do I know is going to show up right here? I know it's going to be a 0. Now, here's why you want to do this. Bring down, multiply, add, multiply, add, multiply. We're in great shape. Okay, what that means is that's a 0. That means it corresponds to a factor of x minus 1. But what about this stuff right here? We did this in R6. What is this? It's the quotient. It's what's left when you divide by that polynomial. Okay? And it used to start with x cubed. Now it starts with x squared. So this is x squared plus 9x plus 20. Now, I want you to take a good look at that for just a second. I'm going to introduce one more vocabulary word. We've pretty well got everything that we need from this section. Take a good look at this. What do you notice about it? it can be factored. Okay? It's a little easier to work with, right? Okay. It's degree 2 now. Do you know how to solve a degree 2 polynomial? You bet. So this factor is x minus 1, and then I'm looking for factors or numbers that multiply to be 20 and combine to be positive 9. The numbers that do that are positive 5 and positive 4. There it is. There's the factored form of the polynomial, and notice that it said use the zeros to factor it. So here are all the factors. I'm going to change colors. Let's write down the zeros. What's the 0 from this one? 1. What's the 0 from this one? Negative 5. And what's the 0 from this one? Negative 4. Good there? Okay, take a good look at this. We're done with the problem at this point. I realize you might have a headache. This is a lot of stuff to keep track of. But notice, what was the degree? 3. How many real zeros could it have? How many did we find? And notice that these numbers, these zeros, check out this list. They're all in that list, aren't they? So, in reality, even though you might come up with 16 or 24, or however many it happens to be, possible rational zeros, do we usually end up plugging in all of them? No, what we do is we find one that works, and then we work with a smaller polynomial. And that smaller polynomial is usually easier to work with. Yeah?
If, let's just say it was an x to the 4th polynomial in the original one, and you had x to the 3rd, could you end up plugging them into that?
Sure. Yep. Yeah. You might end up doing the P and Q stuff or the Q and P stuff a couple times. Okay? The higher the degree, the harder it is. But again, if we peel off one factor at a time, we work with a smaller and smaller polynomial until we get down to something like this that we know how to work with really well. Does that make sense? Okay, last vocab word and we're done for today. This right here is what we call a depressed polynomial. Okay? So the new polynomial that's left once we divide, we call it a depressed polynomial. Okay? It's called depressed, and this is a little cheesy, I apologize. If you were in the 10-10 class, we had things about, the parentheses being married and all sorts of funky stuff like that. Okay, the reason this is depressed is it used to be degree 3. It's a little bummed because it's now degree 2.
They got divorced.
Whatever. The degree is lower. That's the reason it's depressed. Whenever you divide, whenever you factor something out, the depressed polynomial, what's left, is always going to be a lower degree, so it's a little bummed. It's a little depressed. Okay? This is important. The depressed polynomial is usually easier to work with. Okay? Do you have any homework?
Finish
You-
5.1.
Get done with 5.1. You need to go through and you need to think about the stuff that we've talked about today so we can finish it up tomorrow. Have a great day.
Hey, so Mr. Lodge,
What?
I guess the parentheses are polygamous, but they got a divorce from what? But they still have
The
another.
parentheses are polygamous?
Apparently.
All right.
Well, this is Utah.
Very good. Very good.
Okay, we got started in this class. This way, we're going to take it all the way to the top.